it's certainly a privilege to participate in this series of webinars. I I believe these will be ongoing for a period of time, and it's interesting to look at how the performance and longevity of our pavement system is so much affected by durability aspects. It's almost a dominant um, aspect of it, I would say. I'm going to talk about a subject here that I've been quite interested in for many years, and most of my research activities have been related uh, to this, the idea of sustainability and durability and the longevity of the systems we have. I have a strong opinion that particularly our pavement infrastructure does not serve at the level that it could. And many of the projects that we build from time to time are just simply not providing the service that they should be, and they're not providing the level of life or the life extension that the money is spent uh, on those projects. So that's unfortunate, but hopefully we'll get there and figure this out as we have initiatives such as the center here. So I think these seminars are going to be interesting as we go along, and hopefully there'll be many subjects brought up that will be addressed as we go along in time. I'm going to start here with I'm going to probe the left side of your brain here a little bit and see where we go here. But imagine yourself living in this home. Imagine what it would have been like if you'd been living here when this was a brand new structure, when the condition was top notch. The roof was whole and there were no leaks and drafts and so forth. They were probably there now. And as you think about what it would have been like to live here in this home, in this building, do you have any idea of what you would have done to maintain the condition of this home? What would be in some of the activities that you would have undertaken? Had you given any thought to how long this may last, or maybe how long you want it to last? You know, those are, I think, interesting questions. They may be tied to what your purpose is. And are you going to raise a family here? Or maybe this is just something to visit occasionally. Maybe this is a vacation home, and that affects how long you think you want it to last. But these are the kinds of questions that I think come up all the time when we own something and we'd like to take care of it and patch it when it needs patching, repair it when it needs repairing. But what are some of the processes here that could cause this facility such as this to deteriorate over time? Now, obviously what we're looking at here is something that has deteriorated, and who knows how many years old this is, but we can assume at some point that it might have been in pretty good condition, and that over time whoever owned this or lived in it abandoned the place, and things just began to kind of deteriorate on their own. So if we do nothing, this is maybe something that we'll get. But today we have options. You know, we're intelligent beings, and we we can think about maybe what's going on in the environment and the world around us and what we can do to limit the deterioration. Um, One thought here is the effect of moisture. Now, this is primarily a wood structure, and think about how moisture affects the behavior wood. Think about what moisture does to the durability of the longevity. Think about uh, how moisture may affect the factors in the environment regarding wood. Now, we know that there's bugs that eat wood, um, and they depend on moisture. It's kind of an indirect effect. But if you think about moisture and how it affects our infrastructure, it plays an interesting role. Um, so there's probably some science here somewhere that we can start to think about, um, and just on moisture alone. Of course, there's other things here involved naturally that determine how a deterioration process will take place. But in this facility here, in this home, obviously there's moisture from climatic conditions, from rainfall and whatnot. Um, and we know that when um, temperatures are different enough that when a temperature on one side of a wall, for instance, drops below the dew point, we get condensation and we get moisture forming. And so it seems like in one way or another in our infrastructure, moisture comes into play. And that's kind of what I'm getting at today. It could be that the original moisture problem for highways was here. When and here it's not wood anymore, it's soil. And we're we've got a problem here of having to improve the soil layering so we can make it trafficable. Well, again, we see moisture coming in and having a play here on what we want to get. So as far as our pavement systems go, they're often layered, and the surface of the pavement is the one that's got to be the toughest and generally have the most strength. And so we started making our roadways with some type of hardened surface in there so that we could counteract this problem. And that's what the saying of the day was, is get the traveling public out of the mud. Okay, well, we do that, and it seems that we still get into other things that become important that that inevitably affects is affected by the presence of moisture. Now, here what I'm showing in this illustration is a very common type of concrete pavement that's used in many parts of the country, many parts of the world. It's probably one of the easiest ones to construct, and so it's often used. But here we see a slab of concrete that are divided, and these divisions are referred to as joints, and they often run in two directions. We both have longitudinal and transverse joints here. We had the practice has been to put a seal in these and to seal these. And what would be the purpose of putting a seal in a joint? Now, these joints are part of the construction process, and they're made with a saw operation. So these are straight cuts. And because they're straight and they're not meandering, they can be sealed, or they can be filled with the sealant material. And so again, you ask yourself, what's the purpose of this sealant? There are some agencies today that have decided that that purpose is not as important as maybe as it used to be, but nonetheless, there are others that are still filling their joints as they see fit. Now, the sealant is a two-part system. It has a very it's a fairly elastic material. It's either silicone or hot pour that's on the top here, and then it's got a shaping component that we call a backer rod put in there. It's not always installed, but often it is. The conventional practice is to do that. But so these joints here are sealed. But again, I'm asking the question: what's the purpose of this? What would you think would be the purpose of putting the sealant in? I can think of one that I like to talk about, and that is to in fact seal a joint. And seal it against what? Well, seal it against moisture and water that's externally applied to the surface here and limiting its infiltration into the pavement structure. Now, we found that tends to cause problems when we let the water go through. But if that's the case, then why are agencies today not using sealants? Because there's some that say that they don't, or at least it's not in their protocol to practice sealing. This doesn't mention the fact that we do sometimes get cracks in these slabs, and these cracks can be a source of water to infiltrate. And so there is technology to fill these cracks with some type of sealant material as well. But what we're finding is that we can't just consider one aspect of a pavement structure and ignore the others. And if we've learned that water that gets into a structure such as this tends to create problems later on. They're not necessarily immediate, but they're problems that occur over time, and when they do occur, they become very difficult to deal with. And we're almost beyond the point now where we can just allow any of our infrastructure to deteriorate to a condition that requires repair that creates a situation usually that is difficult to fund, much less repair it. And this is why we're interested in longevity. And you think about a concrete pavement system itself, as long as there's enough capacity, a concrete pavement theoretically could last for a lifetime or even longer than that. And some of them do, and we do have evidence that they can do that. So there's really no reason to let our pavement systems deteriorate to a point where they just are almost impossible to repair. It's probably more efficient to determine how to preserve the system rather than let it deteriorate to a great extent. But the deterioration in a concrete pavement is evident here, at least in the cracking that forms and other discontinuities that occur around the joints. And this is why we think it's one of the reasons why we have to seal these up and keep the moisture infiltration to a minimum. Another very popular type of pavement is a continuous reinforced. And I might add that the jointed option here is a whole family of concrete pavements that are built today. And another category is the continuous reinforced. Not all states use this. There's a handful in the US that have found this to be an advantage. Now, I'm pointing out these different types here because I just want to emphasize that the behavior characteristics of a jointed system are quite unlike they are for a continuously reinforced. And I've always said that one of the advantages of this pavement type is its ability to protect the supporting layers from moisture infiltration. I think the capacity here is much higher with this kind of system than it is with the joint. And there's a lot of reasons for that, and I won't get into that in this discussion here, other than to say that this joints that are built into a jointed system tend to move quite a bit, and that makes it very challenging to seal them. We'll talk about that. Here in a continuous reinforce, we're not necessarily sealing these cracks. There are joints there, longitudinally speaking, that need to be sealed, but they're not moving to the extent that a transverse joint in a jointed concrete is. So those are some of the differences there. And I just point this out mainly so that you understand that the behavior of a concrete pavement system is very important here when we talk about its sustainability. In either pavement type, though, there's systems in here that we worry about in design, and I'll just point out some of them here. One is the joining system, which we've kind of talked about a little bit, but then there's also the drainage system of the pavement. That's so important. We haven't done much in modeling drainage as much as we need to, and connecting the dots between that and the durability of the system. But I think we're getting to the point where we can do that, and it's going to come through consideration of the effect that the slab has on the base layer that's supporting it. And this is quite an interesting topic for the concrete pavement community, because there's not a lot of agreement out there right now as to what the best subbase design is. There's still a lot there to be explored, and again, I can't overemphasize the durability aspects of the design of the subbase has on the entire pavement system. I'll try to allude to some of that here today, but anyway, so yeah, we've got different types here, and we've got different systems that are at play. So durability, then, at least one part of it is at the joint. Is an image of a pretty serious condition. I mean, this is not what we want to have to. And if you look here, you can see the joints are significantly deteriorated. In fact, there's probably not, doesn't seem to be a joint there anymore. Whatever's gone on here has seriously weakened the concrete in the vicinity here of where the joint originally was. And you can see a couple, it's almost every joint here. And just imagine now, this being a street in your local community, and your community leaders are thinking about, what do we do with this? I can imagine people throwing their arms in the air and saying, you know, we can't deal with this. Let's just cover it up and bury it, and maybe it'll go away. That's certainly one way to I guess, deal with it. But really, what we have to understand is how to prevent this in the first place. We go to repair these things, and the damage is enormous. It's much worse than we ever, you know, thought could be the case here. And this is just surface deterioration we're looking at here. There's also the underneath side of the slab that tends to do the same thing. And so sometimes, and this is why I mentioned that trying to repair this is almost impossible. We do have ways of going about it, but it's very problematic to do these kinds of repairs and expect them to last for a period of time. Ultimately, what this is ends up being a temporary repair. It's not long lasting, and doesn't add longevity to the pavement system to speak of. It's ends up being a very temporary fix, and it just delays the time that the entire facility has to be demolished and replaced. And that's not what we want. We need to be able to understand this in a better, more effective way. And this is one example of durability. There's others that we've had over the years. I'm just highlighting this one. This is one that I want to do some research on and look into this a little bit more to see what we can do to prevent this. but it goes back again to the presence of moisture and what it's doing. Obviously, there's something very wrong here that's gone on. And can we do something to limit that? If water is being trapped here in these areas, can we do something to limit that? I mean, this is really the question I have when I look at this. So let's just talk about the joint sealant system a little bit. I'm going to just review here with what some of the research has been, some of the research that I've been involved with as well. Just mainly as background information on this aspect of the concrete pavement, but this is again a schematic of the joining system here, and we see again the sealant here. This is in combination with this backer rod that I mentioned before, and this is a way that the material is shaped. Now, it's normally poured in place. There are preformed systems that are there as well. Of course, they don't need a backer rod if they're preformed, but the ones that are not preformed, they're normally placed with this, and it shapes it in a way that we think optimizes the state of stress. And so a lot of the research has been focused on what those stress levels are in the sealant system. In our research, we've gone back and revisited a factor here. It's called the shape factor. It's a very simple geometric term. It's just simply the width here divided by the depth. And it's a way of characterizing the insulation for the material. In our work, we're trying to introduce another factor, another geometric factor. It's called the degree of curvature. I'll talk about that as well, but it's possibly another term that would be useful in the design of a joint sealant system. But again, the agencies have to be convinced that sealing is going to be a benefit to them before they're going to pay any attention to this. So that's one interest of mine is, would sealing improve upon this situation? Okay, that's something to think about. But this is generally what we see with sealants. Here I got different examples, different ages and conditions that are shown here. Some of these pictures I've taken. Here's one I'll just point out here. If you can see my pointer, I'm looking at the right side of this. This is as you can tell, this is a reasonably new, recently constructed concrete pavement, and it's in my local community here, and my city actually designed and built this pavement, and they placed a silicone sealant. You can see the sealant here. It's fairly wide. But what stands out here in my mind, and what caught my attention, was I noticed that shortly after construction, if you can see where I'm running the arrow here and pointing, there's definitely a separation that's taking place. In other words, the assumption that the material is going to adhere doesn't seem to be true. And I haven't said anything about it, but the crack in the slab is associated with this notch that's put in there originally, this saw cut. And this is going to move with temperature changes. So we do see movement here at each joint location, theoretically. And of course, the question is, how much movement can we have? And if we do have any movement, what does the width and depth ratios need to be in order to accommodate that? Well, that's what has always been of interest here, but fairly new here, fairly new pavement system, and yet the sealant here has failed to adhere, and it's basically opened a gap that is almost, it's very similar to what we see here. This is fairly new. This is fairly old. if a sealant performs well over its life, we would expect it to fail this way. Now, this has remained bonded here, most likely, and the sealant material apparently aged. This is what I would say aging would be, but nonetheless, it has formed a failure here eventually. Now, in my experience, this kind of problem doesn't come for nearly 15 to 20 years. There's many years of service that's been involved here. This one is months, maybe weeks. That's premature, and that's a durability issue by certainly, or it's going to lead to a durability. It'll be key to it. Here's an older sealant, another shot that I took. This was on an airport, and I was walking into the terminal, and I just happened to look down and notice the sealant here. There was water standing in the joint well. You can see the water here shortly after a rainfall. And some of the water looks like it's ponding there pretty well, but over here you see this little shiny speck. That actually is a bubble. It's an air bubble that's coming up from underneath. And it was very intriguing to me to see that this system looks to be bonded well, but yet it's leaking. And so, you know, what is going on here? Here's another interesting shot you might be intrigued about. It was to me certainly, this is one of the preform seals that are used. They're the more expensive type. They usually do quite well, and I think they're worth the money you pay to put them in, but there's typically not a backer rod. It's a preformed, it's compressed in place, but something's happened here. We've had some aging take place, quite likely, and the material the sealant has dislodged essentially. I mean, it's just laying in this joint here. The other thing is kind of look at again, the deterioration. This pavement was in a freeze-thaw area, and it's suffered from a type of freeze-thaw damage that has become of interest lately in the Midwest. Very this problem I showed before. And there's more to be said about what I've talked about on the mechanism associated with that. But again, we're seeing apparently some infiltration that's taking place here, and this joint wasn't even cracked. Now, if the idea was, the concept is that we will have a crack with every joint, it doesn't always happen, and there's reasons for that. But here it didn't happen, and yet we still get a serious condition here. This joint, what theoretically was a socket that was not moving, and yet it suffers from this kind of deterioration. So it may not just be climatic effects here, some other things. Now the ultimate failure process is shown here with water in the pavement. I'm going to talk more about this later because we're talking about the joint sealant right now, but just as an aside, we see what water is doing when it gets into the pavement structure. And this, of course, is a shot that was taken by my colleague one day who was out inspecting pavement, and he saw water coming up as the loads passed by and caught it here. And it's just interesting in the amount of damage that's being created underneath with this kind of action. And this is one reason why we see voiding and loss of support. And so that's a durability problem, because the material is having to withstand the effects of water there. And water could have been there for many, many months. But we see a couple of things going on. Here is a discontinuity at the joint. It's supposed to be, they're supposed to be at the same level here. And when they're not, this becomes quite irritating to drive over. It's noisy, it's rough, it's all those things, and it causes a lot of agencies to have a lot of heartache over trying to repair this. These are tough to repair. It normally requires some extensive work, everything from under sealing and slab jacking to removal and replacement. There's all kinds of repairs that have been devised, but like I've said before, these are not long-lasting repairs. They're temporary, and they unfortunately are not giving us the life extension we need. We'd be better off if we could understand this long before this happened and learn to prevent it. Now, I will point out here, I've mentioned the stair stepping, but there's also cracking that's looked at associated with that. So it's another type of crack that we have that's coming in, and we're not always worried about this as much as we should be. This is really an unfortunate situation, but as far as this discontinuity goes and the jointing, some of our studies in the LTPP database have shown that areas experiencing most of the rainfall, their concrete pavements are also experiencing quite a bit of joint faulting. So it really brings into question how effective our joint sealing operations have been. It seems that their effectiveness hasn't been what we thought it might have been, and they're certainly not what it should be. Here's just another interesting picture. This is a picture that I took off the web one day, and I was doing some Google browsing and decided to take a look at a small town, a small community in Wyoming, and I just zeroed in that this community had a pretty good, looks like they have a really good investment in their concrete pavements. And you know, communities, small communities are not really thought to have a lot of money to do things. This was in Wyoming, so I don't know, maybe they're in the coal mining area and they've got lots of energy funding, but it was just, excuse me, it was just, it was interesting to me to see the types of deterioration, and this is a local road. You cannot, the traffic here can't be much more than than local vehicles and garbage trucks and what have you. But yet you see some very characteristic distresses because of the effects of moisture and the lack of durability of the supporting materials. And it's very evident here because you can see these cracks that are associated with that. They've even come in and patched some of these. You can see some patches in here. This is not what we want. This is the you know, this is the effect of this, the problem of durability and the effect of moisture on a concrete pavement across our entire nation. And it's just not in Wyoming. This is everywhere. And our design methods, I think, are not still to the point where they need to address this. And so design has been mainly a structural activity. It needs to be durability as well. And in order to get there, we're going to need to be thinking a lot more about performance models, deterioration processes, and representing them in a way that practical design can be carried out. But if our infrastructure is going to last and begin to last, these are the things we have to start dealing with. So how do we do that? Well, I think particularly on this erosion thing is understanding a process. And I'm going to talk about that probably a little bit more later on because we're talking about the sealant right now. But there is a process here, I think, behind any deterioration, whether it be a bridge, a superstructure, if it's still corroding. I think there is a process there that we can all understand and try to incorporate into improving their ability to design and predict this. But in this process is, first of all, there's water there, and how did it get there? And then there's the material itself, you know, what its resistances are, and then the things that are causing the stresses. In this case, is traffic. These are some of the main elements, and there could be some other ones here, but this is some of the ones that come to mind. And then I will, so while we're talking about it with this process, hopefully we can find the lab protocol to help us determine the properties that are involved in that process. So there's a laboratory component, and then of course the modeling and using these properties that we've determined, and then the performance. Anyway, so I'm not quite halfway yet, and so I've got to pick up the pace a little bit, because I'm only supposed to take an hour for this. So I can see I've taken 30 minutes, so I'm going to pick it up a little bit, see if I can get going. All right, now back to the joint sealant then. One of the things on research is that we've looked over the years mainly at the sealant itself, the material, and how it stretches. And what we have tend to overlook is how this stretching affects the ability for the material to bond to another material here. And in this case here, its bond is what governs the performance. As we saw, as I alluded to earlier, it's not the ability of the material to stretch and elongate, it's the ability of it to bond. And I won't say that it can't bond. I'm going to say that it hasn't bonded. And we have to look at that. Well, in our research, again, I'm not going to spend a lot of time on this, but we're looking again at the shape factor, that. And then we introduced another one here that might be useful, and this characterizes the curvature. So we think there may be another factor here that may become important in the design of the system. I've got some slides here that I'm showing combinations of the shape factor and the degree of curvature, and they are saying about the same thing here, and that is that you can affect the ductility of the system, and you can affect the stress level by manipulating either the shape factor or the degree of curvature. And I won't say how we got different degrees of curvature. It is representing this depth here. We did some specimen preparation in order to do that. But so looking at our test results here, so one of the conclusions that we've come to is that we can adjust the flexibility, which is shown here, which is really the strain level. We can affect the stress level, but the ultimate factor here that overrides all this is what your allowable limit is here. Interestingly enough, if you look at the manufacturer's data, they talk about 100% strain. They talk about 150% strain. But the fact that we're finding is that we can only go to 25% before we're exceeding the capability of the material to bond to the surface of the concrete. Can we improve that? We ought to figure that out, because if we could make a difference. Right now, it's pretty low, I would say. And this doesn't mention, you know, the width of the joint, how deep it is. I mean, this is what the shape factor is all about. And interestingly enough, today, a lot of agencies, if they're sealing, they're only cutting the joints 1/8 of an inch in width, or maybe 1/4 inch. If they cut them 1/8 inch, it's really hard to seal them. I'd say they're probably not sealing. But 1/4 inch is pretty narrow. And when you put, and you try to prepare it for sealing, it's really difficult to do. Another factor in sealing that comes up, not only the distribution and so forth within the material, but it's whether or not we can limit noise, because we know that cutting saw cuts can be a noise factor, and so they'll do some funny high backfilling here. We found that this is probably not a good idea, because it tends to increase the stress levels in the sealant, and then it shortens the ability of it to bond. But again, the backer rod is here to reduce that stress level. And what we found is if you go to this upper band option here, and this again is to reduce noise, you may as well take the bond and leave out the backer rod, because it's not accomplishing anything for you. This dominates the stress picture, and as a result, it debonds at a lower strain. Um, and the backer rod doesn't have any benefit at all. So if you're going to do that, don't worry about putting the backer rod in. You're just wasting money. Another concern that's been again western in the areas of snowfall is the buildup of ice on the sealant, and then the load passes over and pushes it down vertically. We're finding, as you might expect, are going to be very high in the corner, and we need to get deflections here about 80 to 90 mils before this limit here it becomes a factor. So these are just some of the things we've been looking at. I don't have really any conclusions from this yet, but it does appear that there can be an amount of deflection and shoving here that before it becomes a problem on bonding. So we're carrying out bond testing, and I think it's going to change the picture a little bit on how we design the sealant. One thing it is going to certainly point out is we've got to do a better job on getting the bond to occur, because of again, the effect that it has on the ability to resist infiltration. Okay, well, and my running. I got to get going. Another system here that I've mentioned is a sub base, and I don't have enough time here to really discuss it. There's many issues, many factors here that we have to worry about in order to get a durable sub-base system to support, and it's there to support the slab. And here you see a very different configuration of a concrete slab. You're wondering, why is this not flat? That's because it's rare that a concrete pavement is flat. Now, we know temperature and so forth will cause it to lift up and to separate, but there's also a set condition that gets built into the pavement initially, and I don't want to explain that. There's many interesting aspects behind the construction that at least I'm learning now that I think we need to start paying attention to like we have. But obviously, the key to support is contact. We have to have contact between the slab and the base. And if there's water in here that is facilitating a wearing process, we're going to lose contact. So one thing I want to point out is a load deflects the pavement system, it actually causes a wearing to occur along that interface. And this wearing is an abrasion resistance, or it's an abrasion type stress. And it's that wearing that can cause voiding. And if you have water in there that's trapped because of the water that got into the sealant system, it can actually act as a vehicle to transport the worn material away from the interface, and what you end up with is a void. So there's a wearing process here taking place. And again, it's been recognized to some extent already in the ME software, which I hope you're familiar with, but I'm just saying that in this modeling here, they've recognized that this is something that we need to start paying attention to. And I'll just talk about that a little bit, but the thing that's at play here is the bond. And I use the word degree of bond now, and I'm talking about bond strength. I'm talking about cohesive strength, frictional resistance. All this comes into play here, and it's all affected when water is on that interface and acts as a transport medium to carry the material away. And you can imagine if the slab is not completely flat, that certainly worsens the situation. And so this is now a constructability issue too. And again, I don't have time to explain that, but this is a multi-dimensional problem related to durability. And what comes to mind is, what is the test that we can run to characterize the erosion resistance? And this is an example of one test that I've used. And I like it because I can characterize this level of stress that's applied during the testing. And the other thing I like about it is I can get a lot of data in a pretty short period of time, and it's very useful to characterize the capability of a base material, at least to provide a requisite amount of resistance to the wearing process that takes place. Another thing I'll point out in the pavement ME model is this term called wet days. This is again something very intriguing to me because I think it represents the amount of time that water is trapped in a joint system. And right now we don't characterize that too well. I've suggested a modification to an infiltration expression originally developed by Ridgway some time ago and is incorporated in some software that the Federal Highway Administration put together some time ago. But I did a modification to this expression by developing an infiltration component. And I did that when I ran some tests out in the field as shown here. And this is again, I don't have a lot of time to talk about. This is very interesting. It's very simple to do. And as you can tell, it's just a simple falling head. But we sealed these tubes here on the surface, and then we measured the loss of a head over time. And this was at a test site in Arizona. And not a lot of water there in Arizona, but we found that the sealant here in this part of the here was holding up quite well, and it held up so well there's almost no water going through. However, as we went to the edge of the pavement system, to the edges of the lane, and tested that, the infiltration we couldn't keep up with. I mean, we'd pour the water in here and it'd run out immediately. And so there's a huge difference in the durability of the joint just across the lane. I mean, that's another factor we need to pay attention to. But I got enough of this data here that I could calibrate this coefficient here, and it's infiltration coefficient. And we did that here by using conventional hydraulic terms that y'all may be familiar with, but got a very convenient expression here, and then we can use it in the prediction of infiltration. Now, the other factor that comes into play, and I'm getting short on time, but this is a coefficient that is related to the amount of dirtiness that's on the edge of the sealant. And the dirtiness here, as it turns out, affects the ability to bond, and it may be one of the reasons why we see premature debonding in joint systems. But we took that into account, and then of course these expressions can be used to determine the amount of time that a pavement may be saturated with water in the vicinity of the joint. And it's an easy thing to do. We can calculate infiltration and we can calculate the exfiltration based on the characteristics of the base. And using those two expressions, we can determine a probability that the base is going to be wet for a certain time of the year. And that's what my definition of number of wet days is. This is a little bit different than pavement ME uses, but it's the kind of parameter I think we need to get a handle on, so we know what our sealant systems are doing, how much water the pavement is being subjected to year in and year out, and what kind of resistance we have to have. Now, just to help this along, I've got a test site set up in Oklahoma of an approach slab that was subjected to an enormous amount of water over its design that caused it to fail. And we rehabilitated the approach slab by putting precast slabs in that had joints at a closer interval. And I won't talk too much about this, but this is the finished product here. And it's a roadway in southern Oklahoma. And while we were doing this installation, we instrumented it so we could see what kind of infiltration we get afterwards. And the data is quite interesting so far. I'm just showing this is my device here that I capture the water coming out from underneath the slab. you'll recognize it as a tipping bucket. And here we've instrumented the flow of water, and we can see total rainfall versus amount of infiltration. Now, I'm a little disappointed that there is any infiltration, but there is some here that's taking place. So we're tracking that. And again, it's in an effort to model here what the infiltration will be. And so can we seal it up and prevent infiltration? I mean, this is an important question that I think we need to understand. I'm convinced we can, but we'll try and learn more about that. Now, I mentioned dirtiness a little bit because dirtiness affects the bond strength of the material as it affects its ability to adhere to the surface. And so we've been studying that in the laboratory and ways to characterize the moisture level and the effect that it has on bond. And we've done some interesting things here, both non-destructively and destructively. But what we're attempting to do is to characterize the bond strength and contrast that with the stress of the interface. So we've done a lot of finite element work to get that. This is a lot of laboratory work we're doing, and we're running tests, as you can see here, and seeing the limits where bonding is taking place. But the interesting thing about this is that there is, I thought I had another slide here, but I guess I don't. But here, let's see. Yeah, so we're seeing both dirtiness and moisture affect the ability of the material to bond. And so this becomes, again, a constructability matter. And it's interesting how constructability is affecting the long-term durability of some of our systems. And I think we've got to start recognizing that and tying that to the process that we see that's associated with the deterioration. Well, again, it's been very interesting to see the effects here of moisture content and dirtiness on the surface of the interface there. And I had some results here I want to show you, but I guess they're not coming up. Anyway, let me just say that I'm at the end of my presentation here. Again, I want to emphasize the process of deterioration and understanding that and then characterizing that. And that's where we begin to see places where we can apply the science um, of you know, of materials and behavior and so forth to take advantage of that so we can characterize the damage levels and the processes going on. And here's just an example of how the damage at the interface, what its effect is on the interaction between the layers and the result it has on bending stress and design. So that's a great connection. We can then hopefully tie that to cracking models that we use. And this is, again, following the same pattern that's in the pavement ME program, but just enhancing it with you know, a better characterization of the process. Well, we can do something here. I think the potential is very good. We can work out damage schemes and then ultimately come in with hopefully better predictions of what the performance and longevity would be. And that's kind of what our center here is about. So I've taken the bulk of my time. I didn't leave much for questions. I apologize for that, but just in summary here, you know, accounting for the presence of moisture, you know, in a pavement system, it's affecting the joints and the sub base. There's a huge impact here, and it's very much a part of the durability picture. Um, it's interesting how different behavior characteristics come into play, especially on the pavement type, and how that interacts with the ability to drain it and to keep the materials themselves functional and in the strength ranges that we need them to be to provide the life that we have. So bottom line here is we've got to develop a great performance modeling capability. We need to do that, and we want to keep that in mind, I think, as one of the final products here that we end up with. But Anyway, I appreciate your time. I'm at the end of my presentation, and if there's any questions, I'll be happy to try and answer them. If not, I appreciate your time. Thank you.
Thank you, Dr. Zollinger. We do have one question that came in early in your presentation. The question is the mid-slab fatigue crack due to curling/warping cycles, or is it because of traffic load?
Well, that's kind of a loaded question. Nominally, it's the combination of the two. And that's how we've always treated it. But I will say that if we, and I didn't get a chance to elaborate on this very much, but there's also a set factor that that tends to that could dominate that picture a little bit. And if you get too much of a set, then that could lead to a premature cracking situation. But other than that, we take it as a combination, um, and that is probably, that concept I think is still evolving a little bit, but that is basically how the pavement ME program treats it right now, is by combining the two effects.
Okay, great. We have one more question that just came in. Can you explain more about the dirtiness? How do you test and quantify it,
Yeah.
especially the field test method?
Yeah, that's a good question, and that's something we spent a lot of time on. There has been some research done recently on qualifying dirtiness. I'm not particularly happy with them, and I'm not sure the people that did the work are either, but nonetheless, there have been some ideas out there. But there's been a number of things done: finger wiping, pull tests of different in the laboratory, or pull tests in the field. But what I like the best is what we've tried to do, and that's to do a textural assessment of the interface. And this is quite easy to do. You can actually do it with your cell phone camera, but you can get enough density in your image where you can see the texture. If you use a pixel analysis software, you can characterize the pixel shape of that, and you can decipher the level of dirtiness. Now, you'd have to also keep track of the amount of dirt that you have on the interface, and we do that by concentration. And so you keep that information and your texture numbers, and you can do some amazing things with that. I like it because it looks like, to me, it's first of all, it's non-destructive. It can be done very, very quickly, and it can be done over a wide extent of a project, and that would be invaluable information for the installers. And that's what we need to get to, is that kind of thing, I believe. But anyway, we're doing it with imaging. That's how we've been able to do it. And it seems to be so far so good.